And we're back. A moment ago, I was just geeking out over how cool calculus is. Now we're going to introduce a related concept. Take a look at this graph for a moment. I want to show, now that we understand that slopes are rates of change, so here it's decreasing, here it's increasing, and here it's increasing very quickly, and here it's dropping like a stone. Well, I want to name 7 or 8 definitions. Don't worry, they're not bad. They're all very easy because they're all the same as their English meanings. In fact, I've already said 2 of them. Here, where I'm drawing green, the graph is increasing. And so it's also increasing here, and it's also increasing again here. And I think you can guess what the other one I said is. On these red curves, these red parts of the curve I'm drawing in now, here the graph is decreasing. You guessed it. What else can we say? Oops, 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 oh my goodness. Whoa, that's flat. That's a third kind of rate of change. It's not increasing, it's not decreasing. What would you call that? Still, motionless. We're going to say constant. Okay. Now, there's a few special points on this graph, the hills and valleys. Right up here, the special thing about this point, how about pink? I have as many colors as I could possibly want. I'm going to use pink. This point right here is special because it's taller than any of the other points around it. Now, it might not be the tallest point on the whole graph, but it's certainly taller than any of its close friends. And that's because leading up to it, we were increasing, and as soon as we pass it, we start decreasing. We call such a point a local maximum. Maximum because it's the biggest, local because it's the only the biggest in its neighborhood. Once it goes to the big city, it's not special. But over in this small town, it's real special. So this is a local maximum. Actually, this point here is also a local maximum. But in addition to being a local maximum, it's actually real special. It is the absolute maximum. It's the best thing there is. It is the highest point on the entire graph. Have you ever thought about why humans have an up is good and down is bad metaphor? Like rising in the workplace, or good rising tweet, or falling ratings. Why do we always think that up is good and down is bad? I'm told English isn't the only language where we do that, by the way, so something to explore if you're a linguistics major. Maybe you can clue me in. Just like I have local maxima and absolute maxima. Yeah, that's a good shade of orange. This point down here is special for a different reason. It's the smallest point in its whole neighborhood because we were decreasing leading up to it and then increasing afterward. So he is called a local minimum, the smallest thing around. And then it's not the absolute minimum because down at this end of the graph is the total pits. So that point right there, what color haven't I used yet? How about a nice scarlet? This point right here, come on, there we go. This is the absolute minimum. So see, all of these words mean exactly the same thing as they mean in English. Those are the 7 definitions I wanted to show you. Nothing so bad. Now what I'd like to do is just go up to our toolkit functions and apply these definitions to them. And so we're going to take a look at these 7 definitions and ask, well, how do they look? So in this class, I just ask that you be able to take note of where these things are on a graph, label a graph with these terms. In calculus, another side effect of the amazing beauty of calculus, shown here, come on, Another side effect of the amazing beauty of calculus is that since you have a formula for the instantaneous rate of change, a formula for the slope at every single point, what the speedometer shows, you can point out exactly where it is that the speedometer shows 0. And since it's decreasing up to there and increasing after, that point exactly is where the minimum is. So if you take calculus and you learn these simple tricks, then you'll be able to say, oh, okay, the minimum is wherever 2a plus 3 is equal to 0. Well, I can do that right now. 2a plus 3 equals 0, does it? Well, then 2a equals -3, and a is -3/2. Well, since the roots are at -3 and 0, the fact that the minimum is right between them at -1.5 shouldn't really be a surprise. But on a graph like this, we'd be hard-pressed to find the answer without calculus. So, yet another amazing tool in the arsenal of calculus. Again, the contribution of Leibniz and Newton to humanity cannot be overstated. Also, they were total jerks. They hated each other. Brilliant, but jerks. In fact, they hated each other so much that even after they died, their fan clubs kept fighting for 100 years. So the constant function. I bet you can guess. This function is constant on all real numbers. It's in the name, come on. It's flat everywhere. It never changes. So it never increases, it never decreases. Now the identity function, which of the three is that doing? Increasing, decreasing, or constant? That's right. It's increasing. Can I just write INC? It's increasing on all real numbers. If I wanted to be fancy, I could write out the interval -infinity to infinity, but I'm not going to. It's increasing on all real numbers, but how about the absolute value function? Oh, this one's special. It's increasing on the positive numbers, 0 to infinity. It's decreasing on the negative numbers, -infinity up to 0. We always go left to right. So -infinity up to 0. And that means that right at 0, 0, pink it is. Bright pink. We have a local and absolute. It's both local and absolute at the point 0, 0. So, do you think you could fill in where the quadratic function is decreasing, increasing, and has a local or absolute minimum? Well, both specifically. That's right, all the same places. Moving on. The cubic function. Pretty simple. It's always increasing. The reciprocal function. Oh, that's weird. You know, it jumps from tiny to huge, or it jumps from very negative to very positive, I should say. And yet, if you look closely, it's decreasing here, falling, 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 and then it jumps to infinity, and then it's falling, falling, falling. So, you're tempted to write decreasing on all real numbers, aren't you? But it's not, because it's not defined at 0. It's only decreasing on its domain. So I'm going to write that decreasing on -infinity to 0, union 0 to infinity. I wish there were a less annoying way to write that one. There's not. Maybe you could make one up and convince everyone to use it. I would thank you profusely. If you can convince all the mathematicians in the world to come up with better notation for this and then use it, I'll give you an A. The reciprocal squared, f of x is 1 over x squared. Well, this one's different. It's increasing over here, and then it's decreasing back down over here. It jets up all the way to infinity, it has a little jump, and then comes all the way back down from infinity, all in a finite amount of time. So it is increasing on -infinity to 0 with a parenthesis, because it's not defined at 0. there's that parenthesis. And then it's decreasing on the cut, copy, paste, delete, share. No, it's decreasing on 0 up to infinity. So this second half of the curve. The square root is increasing, well, on its domain, but not off of it. I'm going to be a tiny bit pedantic here. I'm going to write 0 with a parenthesis. And the reason for that is technical. We're just always going to write increasing and decreasing with a parenthesis. If you want the technical reason, it's because to find out whether it's increasing or decreasing right at this point, I have to use a calculus limit derivative. And the limit only works if you have some space on both sides of the point. We don't have any space to the left, so we can't say what it's doing at this point. I know that's hugely technical, so that's why it's never going to come up on a test. The tests are multiple choice, and your options are going to include this and not that for increasing. There you go. This last one, well, it's increasing everywhere. You see it, right? It's always moving up. Moving up in the world. There's another one of those. Up is good, down is bad. Why? Well, that's it. We did it. Unit 2 is over. See you in office hours.